Okay, so for the second talk today, we're very happy to have Marko Simonovic, who will tell us about prospects for new physics from galaxy surveys.
Okay, thank you. So first of all, I would like to thank the organizers for the invitation. It's very nice to be here, actually for the first time. And yes, they asked me to say a few words about possible new physics from galaxy surveys, which, okay, I'm going to basically do a very broad description of things that people have been thinking about, and hopefully it will inspire some of you to think more maybe about some other applications that we were not considering so far. All right, so first of all, just to have everybody on the same page, these galaxy surveys are they come in different flavors, but what I'm going to talk about in particular today are spectroscopic surveys, where we are looking at the sky and we are making a map where we have direction to the galaxy. So each, for example, this is a particular example of a survey, which is now more than 20 years old, and it has roughly 100,000 galaxies here. So you look at different directions on the sky, you measure the redshift to a galaxy, and you produce maps like this. Now you can see even by eye that galaxies are not distributed in space in a random way, but instead they produce some patterns, the so-called cosmic web, and their distribution is not completely arbitrary or given by some very nonlinear dynamics, but also depends on initial conditions for our universe. And in a similar way, the CMB, it contains a lot of cosmological information. And so then the idea is that, or the question is, how can we extract this information? What type of things can we think about? What can we learn from these kind of maps, etc.? Now, we are very good in making these maps. We are staying on this exponential line, where basically every decade we increase the number of objects to which we measure spectra by a factor of 10. This has been the case for the last 5 or 6 decades. What I showed in the previous slides was, for example, something from the end of 2000. In the meantime, probably you heard about BOSS data, which is currently the best available data set with a few millions of galaxies. And there are ongoing surveys here in orange, such as DESI or Euclid, which are going to collect spectra to roughly a few tens of millions of galaxies. And already there are plans for MegaMapper. So all of these things are going to happen in the future. And now the question is, okay, can we use it for something interesting in the context of new physics, or and what kind of things can we think about? One thing what is important is that there is a particular line here that I drew, which corresponds to the number of independent pixels that we can measure in the CMB. And while these two things, the number of galaxies in your survey and the number of pixels in the CMB should not be compared directly, really, they give you some sense of how do these different probes compare in terms of their statistical power to constrain cosmological parameters. And you see that this is a special point because for the first time, these galaxy surveys are going to have some comparable statistical power, and they will become very interesting, I think, in terms of constraining cosmological parameters. Okay, so then the question is, what kind of new physics can we expect to learn? This is a very particular kind of probe, which is not, it's not obvious how does it relate to the underlying particle physics models. And I think that it's fair to say that, first of all, I don't know to what extent any of these things are new physics. I mean, they certainly fall into this category, but also they have been discussed quite a bit. I don't know, for sure, many of you have seen many of these things before, but I think that roughly speaking, there are two types of things that one can use this large-scale structure for. One is that is to really constrain better initial conditions. So we are going to put certainly better limits on various things. And here I'm listing some kind of questions that are interesting, and we can give some quantitative answers to these questions better than what we can do now with the CMB. Those include whether the question is whether we have single or multi-field inflation. Is the speed of density fluctuations during inflation the speed of light, or they're moving slower than that? Various more exotic options, such as spectroscopy of massive and higher spin particles that may exist, and it can be probed if the energy scalar inflation is high enough, paramoidal features in the power spectrum, etc. So these are all a certain class of questions that relate to the initial conditions, and galaxies remember these initial conditions, so they're useful for that reason. And the second reason is that all these large-scale structure surveys are particularly good in probing gravitational interactions, and since states, then if you have anything which is not the standard lambda CDM, you will start probing that or being sensitive to this. And one clear example of something that will happen for sure is the measurement of the sum of neutrino masses. But then in a similar way, and I'm going to show some plots, you can constrain other massive but light relics, ultralight axions. You can make a very detailed measurements, which are at least order of magnitude better than what we have today of the spatial curvature, which if it turns out to be non-zero, slightly negative, let's say, would be an interesting consequences for inflation. Also the expansion history, and in particular, the equation stated dark energy, checking really to what extent it is something like a cosmological constant. But also, I think that's something that hasn't been discussed very much. You can really put various constraints on various new energy components, which for whatever reason, to solve some tensions or just for the purposes of exploring some options, you can put either in the early or the late universe. And so finally, you can also probe dark sector, and there are various options there, but one that I'm going to mention briefly is, for instance, what happens if you have some new long-range interactions with the dark sector, and how that can affect, for example, the distribution of matter and galaxies, and how can we use it to constrain these kind of things. So this is some kind of a list of things that, or typical kind of things that we can talk about. All right, so but you have already seen all this in the context of the CMB, and the question is why this CMB is not good enough. There are two main reasons. First of all, in the CMB, the cosmological parameters determined fitting this angular power spectrum of temperature fluctuations, polarization fluctuations, etc. And the output, the error bars are given by the error bars on these measurements, which in turn depend the number of pixels on the CMB that we can observe. And for some typical L max of let's say a few thousand, the typical number of pixels is roughly tens of millions. So this is the line that I was showing before. So there is some ultimate bound from the CMB that we cannot surpass. And the second reason why the CMB, we should always remember the CMB is great and it is super constraining for lambda CDM. But when we start the extensions, then what can happen sometimes is to open up these strong degeneracies where we may lose a lot of constraining power. So for instance, these are some famous examples. I'm showing here, for instance, what happens if you allow spatial curvature, and you can see that the primary CMB then has this big degeneracy, and you have to use some external information, such as BAO, for example, to nail down the omega matter, omega lambda. Similarly, there is a strong degeneracy between the Hubble parameter and the sum of neutrino masses, if you consider only CMB, and again, adding the BAO information from galaxy surveys helps. Or for instance, a lot of discussion now is happening about ineffective and constraints from the future CMB experiments such as S4, but we should remember that there is also strong degeneracy with the helium fraction, and here what is shown is what happens when you combine again with the BAO. Otherwise, constraints are much weaker. So these are two main reasons. CMB is great, of course, it has been the pillar of cosmology in the last couple of decades, but it has a finite amount of information, and we are approaching the point where we are going to harvest all of it. And second, that is the degeneracy that we have to break with some external data. So one thing that has happened recently is that we we are able now to, I'm not going to say how exactly and why, and I would be happy to discuss this with you if you really want to know the details, but we are able to really complete the evolution of cosmological fluctuations all the way from some vacuum state in inflation or to the CMB, which was done already in the 80s and 90s. And then finally, we can do something similar for the galaxy distribution and large-scale structure. And this is this effort has culminated in really writing a few publicly available basically nonlinear codes, which for any input of cosmological parameters or any cosmology you want, can predict for you the nonlinear correlation functions for the galaxy density field. So they're similar to what happened in the CMB, where people wrote CMB fast or CAMB or class, etc., and they really work in a similar way. So you can give some cosmological parameters or your theory as an input. As an output, you're going to get, for example, the nonlinear galaxy power spectrum as observed in redshift space, etc., etc., etc. So now this is very important because it really allows us to explore various theories, to do MCMC analysis with the large-scale structure data, and for the first time, really see what kind of constraining power can we really expect from these surveys in an honest way without relying too much on the CMB. All right, so as just one example, let me show you what happens when you apply these new tools to, for example, currently existing BOSS data. I already showed you that the BOSS survey has something like a few million galaxies. And what you can do is to take various data chunks. They observe parts of the sky in the north and the south at various redshifts, etc. I'm showing here one particular data chunk, which is the North Galactic Cup at high redshift. And you can measure the two-point correlation function or its Fourier transform, the power spectrum, which is shown here. This correlation function is anisotropic because you have some preferred line of sight, and since you're measuring things in redshift space, there are so-called redshift space distortions, and this is why what is shown here is both the monopole and the quadrupole of the power spectrum. And the same way as we do in the CMB, you can just fit for cosmological parameters, trying to given the cosmological model to find the best possible fit to these data points. Okay, so this hasn't been done before. In the past, the way that this data was analyzed is to use the so-called fixed template analysis, where you would assume some linear theory, fix cosmological parameters which determine the shape of the linear power spectrum, and use this data only to measure the amplitude of the power spectrum and frequency of these BAO wiggles, or in other words, position of the BAO peak in real space. So this is known as geometry plus growth, or you're basically constraining some particular combination of these parameters. But what the detailed knowledge of and understanding of how to predict these curves gives you is that now you can use the full shape and get all cosmological parameters, and crucially without any input from the CMB. And so there were a couple of analyses in the last couple of years where this was done for the first time this way with the BOSS data. And interestingly enough, you can see here that, of course, maybe we can focus on red contours, which are Planck measurements, and also, let's say, blue contours, which are BOSS measurements. You can, of course, see that the CMB is still doing better for many of the cosmological parameters, particularly the amplitude of the power spectrum and the spectral index and so on and so forth. But some of the things, such as Hubble parameter or omega matter, are measured with a similar precision as the CMB. And that is very interesting because it tells you that we are entering, even today, we can give some independent measurement of the Hubble parameter using completely different redshifts and completely different data sets. And remarkably, these data sets are consistent. So that was also, well, they should be, unless the CMB is correct, but since they have completely different systematics, they're taken in a completely different way and so on and so forth, it is not entirely obvious. It is an important milestone and a proof of concept that we can really do this, and the same pipelines will be applied to the upcoming galaxy surveys that will deliver their data in a couple of years. All right, so, okay, so now let me go to the part of the talk where I'm going to show what kind of things can we expect with these surveys which are currently collecting data, such as DESI or Euclid. So let me first take a look at the simple example of just lambda CDM, because I want to illustrate one point. And so if I do the similar analysis where I generate some fake mock data, which roughly speaking have the same volume and the same number density of galaxies as this Euclid or DESI, and I analyze them in the same way, what I can see that here, what is shown here is again various cosmological parameters in lambda CDM plus the sum of neutrino masses now. And different contours are the following. Maybe you can focus on this dashed line, which is just the Planck contour, and then red contours are just given by the power spectrum measurements from these future surveys. And you can first of all see that these two contours are comparable to each other. This is what I was saying before, that we are entering this era where these galaxy surveys are going to give comparable constraints on cosmological parameters, whatever your theory is. And the second important thing is that they're very orthogonal to each other. And this is the most important point. So for instance, look at this square here. I think that the resolution is not very good, but this is the Hubble parameter. And this is omega CDM. And both experiments have similar constraining power, but when you combine them, you get this tiny little blue blob. So you're getting measurements which are 5 to 10 times better than each individual experiment by itself. And this is the important difference compared to what we have today. So this is not some far future.
Does this mean, can I ask a quick question? Does this mean that the theory systematics essentially don't matter at this level yet, or that they are also improving going from the older survey to the new ones by getting more data?
So you mean theory systematics in
the nonlinear part, right?
Yes, I think that all that I'm showing here is tested to the level where no theory systematics matter. So I think that we do believe theory at this level, yes. I think that this depends a bit how aggressive you are in your data cuts. So if you go more to the nonlinear regime, clearly you're going to be more sensitive. I think that for the upcoming surveys, such as Euclid or DESI, we'll be able to achieve these error bars without having to worry about theoretical uncertainties. Yeah. Now, going beyond lambda CDM, you can see the same pattern. So let me see. So here I'm showing just one example, even though you can think of many. And this is the example of early dark energy. As some of you may know, this model has been introduced as a solution, one of the possible solutions to the age-naught tension. And the main idea is to modify the energy density content in the early universe, or to modify the expansion history at the 10% level around recombination in order to change the sound horizon by 10%. Now, of course, doing that, you have to also modify other parameters such as omega CDM, etc., and move them compared to their standard lambda CDM values, which it turns out you can do if you have only constraints from the CMB, which is shown here in these green contours. Then you can really like get away, or at least reduce this tension to some acceptable level. But if you include also the information from the full shape power spectrum analysis in red, then you can, maybe here it's not entirely clear, but you really go back to the point where this model is ruled out. So this is one example of some extension of the lambda CDM, where even with the current data, including this large K structure, makes a difference. And if you go to now do some kind of forecast for, again, these upcoming surveys, then you see that compared to the CMB, which is now given in these blue contours, like adding, for example, the mock Euclid data really nails down parameters so much that either you're going to discover something or completely rule it out. So very often people talk about the resolution of the Hubble tension in terms of measuring things from gravitational waves, et cetera, but much before any of these things become true, we're going to have data so precise that there will be no room to move anymore. And so we're going to know if the tension really can be resolved by some modification of the CDM, or it's really most likely the systematics in some other measurements. Yeah. Yes.
Which one is it here?
What we used here in particular is the original model proposed by Marko Simonovic and collaborators. I think that it doesn't matter so much because the only parameters that really matter phenomenologically are what is the fraction of this early dark energy when it peaks. No. And effective is radiation, extra radiation. This is really extra dark energy, which all of a sudden disappears around recombination. So there are two parameters. One is like how much of it you have, let's say 10% at recombination. You need some amplitude, and you need really the redshift where it decays, and perhaps one more parameter to adjust some slope or something like this. So it's like a phenomenological model, which there are various then reincarnations and particle physics models that people try to invent, which are maybe more desirable from the model building point of view. But in a nutshell, it's this, and these fluctuations are sensitive broadly. I mean, my point here really is to illustrate that if you inject any kind of new energy component, you can get away today with roughly 10% of new things. In the future, near future, it will be 1%. So it's a big improvement in this direction. And you can see it also in other examples. For instance, I put two papers which are recent. So then I think that it was kind of interesting. One, for example, is the constraint on ultralight axions. So for example, here the masses are really smaller than 10 to the minus 25 so 22 electron volts. So these kind of ultralight axions for sure cannot be 100% of dark matter, but they can constitute a fraction of dark matter. And then the question is like, how much room do we have? How much axions can we accept? Clearly, the problem is that so the way that it works is that axions have some de Broglie wavelength. They prevent structural formation on scales which is inverse of the mass, right? And you're introducing some kind of a scale dependent shape in the matter power spectrum, and the depth of this suppression depends on the abundance of these axions. So this is how you can put constraints, for example, from the CMB or large scale structure generically. And what is again shown here is what happens when you do the CMB analysis. So this abundance of these axions relative to the dark matter is very much degenerate with the Hubble parameter. Unfortunately, it goes in the opposite direction from resolving the agenal tension. So maybe this is why I didn't hear much about it. But again, this degeneracy gets very effectively broken by adding galaxy clustering from the full shape analysis that I described before. So you basically improve these bounds by a factor of 2, just adding the data that already exists, analyzed in the proper way. The same thing in this other paper, we studied how well can we constrain, for example, the light but massive relics. So their effect is again very similar to neutrinos, except that since they decouple a bit earlier, they're a bit colder and their abundance can be lower, so you can get masses of order of a few electron volts as an upper bound. But again, my point here is that, for instance, these combinations where you really add the full shape of the galaxy power spectrum from Bose really add a lot. Yes, exactly. There is a strong assumption here that they decouple as early as possible. Yeah.
Okay. They decouple as early as possible.
Yes. So that they have the lowest possible temperature, right?
I guess that's the most conservative thing.
Yes. Yes. So they decouple very early, and then basically their contribution to an effective is relatively small because there are so many degrees of freedom to still go out of thermal equilibrium, and their abundance also is relatively small, right? So this is the underlying assumption to make this plot. Of course, if you open this up, it will be more complicated. You can still put constraints, just that. But this is just to give you a flavor of some kind of things that we can think about, okay? And nowadays people think about it and it's possible, and until 2 years ago it was not possible. It will be even more exciting in the future. Yes. This all has to do with the number of degrees of freedom, I think. I have to remember.
I would have imagined that this makes a factor of 2 or 4 different.
Right. I don't remember. Yes, I'll have to think about it. And you know, I don't quite remember why there is such a big difference. You're right that. Yeah, I don't remember on top of my head.
That's all right.
Okay, so everything I said so far was based on this very conservative thing. Like, let me just measure the simplest thing, which is a 2-point function, which is called the power spectrum of Fourier space. I compare it to my theory, I constrain things, and all the numbers that I showed you, and this plot that I showed you is based on this. Maybe just for fun, and like let me maybe tell some story which is not very conventional. You don't hear this very often, and actually it's rather old by now, still not used very much in practice, but I think that it has some potential in the future. And this is like the story of higher order endpoint function. Of course, one can tell you, I could tell you about modeling of the bispectrum, doing these kind of complicated things where some details of how do you really calculate everything matter, and there is a lot of uncertainty, theoretical uncertainty, etc. But let me show you like the benefits, at least we have in cosmology, from some kind of features or non-perturbative results combined, and how does it work. So in large-scale structure, there are these like relations which are called consistency relations, and they're essentially the equivalent of soft theorems for gauge theories for the scattering amplitudes. They're derived basically in the same way, and they have the same underlying logic, and they're exact, meaning that they really hold beyond some perturbation theory, and of course also in the nonlinear regime. And so one such statement is that if you look at the 3-point correlation function in this particular limit, when one of the momenta is much smaller than all the others in the soft limit, then this ratio must be some smooth function of k, which starts as a power spectrum of k, and then it has maybe some corrections. And of course, it's analytic in Q, so it has some higher order corrections in Q. Okay. Now, these theorems can be derived under following assumptions. The first is that you have single field inflation. Second is that if you have some kind of effective equivalence principle. I will explain what does it mean. And the third thing is that there are no features in the primordial power spectrum. Okay, so maybe it is unclear why these assumptions have to do anything with the soft theorem, but this is true, and I'm going to show you now what happens if you violate any of these assumptions. Okay. All right. So first of all, if you do have some features, I'm very briefly going to mention that then what happens is that this feature actually is producing some terms in the nonlinear 3-point function, which is calculable. So you may not know what is this thing exactly, some smooth function of k, but whatever is the wiggly function of k can be exactly computed, and it is given by this formula. This is related, of course, in our universe, we do have a feature. It is the BAO peak in the correlation functions, or wiggles in the power spectrum. And so this is exactly the type of formula that you get in the real world, and it is connected to the so-called infrared summation, which you have to do in order to describe the nonlinear evolution of the BAO peak. Okay, so here what I'm showing is that how this BAO peak in the correlation function in real space looks like in the linear theory, and after some nonlinear evolution happens, then you have these data points, for example, taken from simulation. And in order to calculate this change, what you have to do is to take into account all possible long wavelength displacements that are moving galaxies around, and those are intimately related to this particular soft limit in this particular way. I don't expect you to really understand this formula. I'm just saying this as an example of something that exists already today, but of course, we may have primordial features also from other sources, not just BAO, and then the same logic will apply. All right, then if you violate the assumption that you have a single field inflation, what that actually means is that your small scale power spectrum in the presence of this long wavelength background can now depend also on the gravitational potential through the dependence of the primordial amplitude of the power spectrum. The gravitational potential is induced by local non-Gaussianities. And if this happens, then you're violating this kind of analytic structure in Q, and you know that the leading term in the soft limit goes like k squared over q squared. And this is a very particular feature in the bispectrum which cannot be mimicked by any astrophysical processes. So there is no galaxy formation physics which is going to produce such kind of behavior if it obeys the equivalence principle.
Is it still true if you have heavy fields during inflation that couple to the inflaton? Or do you really need the two light or flat degrees of freedom?
Yes, you need light or flat. If you have heavy, there are two things that happen. If the mass is below certain threshold in terms of units of age, then this power is going to change. There will be some correction, which depends on the mass of the fields. There will be some power delta here, which interpolates between, I think, basically interpolates this thing between -2 in the dimension of Q and 0. And if the fields are more massive than this, then you're going to get this. I'm going to show a slide about that.
Okay.
I'll come back to this. But
Related to the equivalence principle.
Right. So here, like, so the equivalence principle, like in the basic. My basic assumption is that nothing depends on the gravitational potential itself, but only on the second derivative of the gravitational potential. That would be the equivalence principle. And dynamically, this is true in our universe, but in the initial conditions themselves, you are like, if you have a single field inflation, you have a coupling of the long wavelength phi with the short wavelength phi's, okay? So you're changing, for example, the amplitude of the power spectrum of small scales depending on the value of phi in the patch where you're looking at the power spectrum, okay? So you're basically violating, in a sense, the equivalence principle in the initial, setting up the initial conditions. It's the same like having like the elevator or the rocket, where of course you will feel the same things, but then basically, depending whether you're in the rocket or the elevator, you give different initial conditions to the system. Of course, the evolution will follow the equivalence principle, but the initial conditions break it. And this is what happens in multi-field inflation. I think that tracing it back throughout the evolution, all the way to inflation, it essentially tells you that there is something other than gravity, which determines the initial conditions in this sense. And this is why we always have to add some second field, or in a sense, some new interaction to be able to produce such results. But however, there is also you can think, and this is probably the most, first of all, here let me just say one thing. The fact that this is a very particular feature, which is not degenerate at all with astrophysical evolution, is what allows us to claim that we can measure local non-Gaussianities very well from galaxy surveys. And
For that matter.
so I'm going to come to this in a second. Yes. So assuming that we are looking for this particular shape, we know that no matter the nonlinear evolution, the standard physics will never produce it. And then it means that if I look at these different constraints on FNL, here it's given as a function of redshift, assuming that I observe half of the sky, blah, 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 blah. But like you can see that we can go below 1 and it's not so difficult. And I think this is true. And different curves here represent different theoretical models. For example, the ideal survey is the one in which everything is perfectly known and there are any uncertainties. And then, for example, this solid blue line, which is here, is basically nothing rather than just a 3-level bispectrum. And you can see that there is no big difference between the two because you're not paying the price of marginalizing over various parameters, Nuss's parameters which describe galaxy formation, simply because this shape is so orthogonal to everything else. Okay. And finally, I could not resist not to include some reference to Galileo, given that I'm around. Let me come back to maybe this question. What happens if, for instance, which is a speculative idea, but it can well be, for example, the dark matter particles have some long-range interaction, let's say, and which now acts a bit like gravity, some additional, basically, for the purposes of Galileo, they experience slightly different G Newton. And if Galileo was to throw away two galaxies in a universe where there is no such force from the Leaning Tower of Pisa, they will, of course, fall down with the same acceleration. If, on the other hand, he would to do it in the universe where, for example, dark matter particles interact with other dark matter particles a bit differently, then, for example, if there are two types of galaxies, for example, blue and red, and one of them is dark matter poor and the other one is dark matter rich, in other words, the fraction of baryons compared to dark matter is different, then they will fall with different acceleration in the external gravitational potential. And this then violates dynamically the equivalence principle. So there is no fundamental violation of the principle, but effectively, what happens is that you're breaking this theorem, and the corrections you can show are going to be of this type. So they don't go like 1 over q squared, but rather 1 over q. The reason is that here you're sensitive to the gravitational potential in the initial conditions, and here you're sensitive to the gradient of the potential, which is providing acceleration for these objects. And this is why it goes like only 1 power of q, and it has this particular angular dependence. Okay. So for instance, measuring all these galaxy surveys and splitting galaxies into two types by various properties A and B, and calculating this cross correlation and searching for this kind of angular and scale dependence, you can put constraints on this parameter, which in a sense is delta G Newton over G Newton. I think that you can do much better than with the CMD, for instance.
What does that mean? Sorry, I don't
It
know.
means, well, it is the best that we can, because how else would we put constraints on such long range
What is
the dark sector?
Virginia?
Okay, let me say 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. Sorry, 2? Self-interactions are very different. They will never, self-interactions will not produce this type of behavior, because self-interactions are a bit like having pressure in the dark matter, the dark sector. They have to do with like motions of particles, you know, above some scale. They're not active, and this scale has to do with the typical size of the halos and so on and so forth. So this diverges as 1 over q. So this gets bigger and bigger as you consider larger and larger scales, because everybody falls in this long wavelength gravitational potential. So any type of self-interaction will fall under the assumptions of the theorem.
So it's
yes, but this is all on very small scales. I'm talking about large scales.
How small, precisely? Sorry, because.
Oh, thank you. Yes, I knew that Galileo will always be the best thing. There is no question.
So how small?
Right. I don't know that there is such constraint to the bullet cluster, because usually people put constraint on the self-interaction of dark matter. But like you see, this is a bit like gravitational 222. It's very small. You cannot really talk about. So imagine that so if you correct G Newton by 1%, you will not see it in the bullet cluster. Here, I think on cosmological scales you will start seeing it. I think, yeah.
But is it?
But this is really about like some. So maybe just for the scales, what really matters in this analysis is there is a separation of scales, and I'm assuming that this momentum q is large enough that I'm in the linear or quasi-linear regime. So as long as this q is like something like 0.1 or smaller, k can be anything which is larger than that, and I can go like as far as I can. Basically, at some point, there will be the issue there is a shot noise and I cannot measure anything anymore because I run out of galaxies.
But like on cluster size, or
it doesn't matter. This is a number. This statement is true even in this very room. But unfortunately, there are other forces here which prevents us from testing this. So if you come to the cluster scale, there will be a lot of baryonic feedback, blah blah blah, that you have to disentangle. So I think that with case you can go all the way to the nonlinear scale, the typical intergalactic separation.
I see.
Yeah.
So ask, is this a bound only on like forces? If you have, let's say, charged particles that have like gauge interactions, or
you can. I think that it can be phrased in various ways. Here I have some very basic thing in mind, because if you change scalar field, then of course it's attractive.
yeah.
If you have like vector boson, then of course, for example, some U1 interactions in the dark sector. If the medium is neutral, then you cannot do much. So we have to find a way to, for instance, make it so to produce some asymmetry in the dark sector, such that, for example, you have more, let's say, negative than positive particles, and then also the mediator could be the vector boson.
You're effectively assuming some sort of massless mediator,
Right. So,
because you have 1 over q over.
Exactly. So here, what is assumed is the mediator, which is maybe not precisely massless, but light enough that on very large cosmological scales it still looks. Maybe it's like not. Let's say it can, for sure, it can be, the mass can be the Hubble scale, or a bit larger than that. But you want it to have this 1 over q on a relevant scale. Yes.
But you said this has q definitely been in the linear regime still, or even for collapsed structures.
I think that in the collapsed structures there will be many things that prevent you from doing. For example, in this very room, we have the Earth, which provides the gravitational field, and so on and so forth. So the same logic will apply.
Can push q? I guess that's my question.
I wouldn't push it to believe this formula. I wouldn't push it beyond quasi-linear regime, so point q, 0.1, 0.2, 0.3, whatever. Sorry, I think that I'm running out of time. So, but basically, this is. Let me skip this.
Yeah, you can continue. You still have time.
I don't. Well, I never know if. Yeah. Here. Okay, this is another example, which galaxy.
So one about the previous. So what if you had like a violation of? So this is like comparing the equivalence principle between baryons and dark matter. How does it? What is this equivalence principle comparing? Is it dark matter relative to baryons? How they fall under gravity?
Here, I want to be vague on purpose, because I don't have some. I can invent some particular example. For instance, if you want to talk about baryons versus dark matter, you cannot separate them in galaxies, but you can find galaxy sample, which, for example, is baryon rich. It has a bigger fraction of baryons compared to dark matter, and a galaxy sample where it's the opposite. So then, effectively, you have these galaxies A and B. Or, for instance, this can refer to some fifth force, which is screened in some way in massive objects, which is light objects. It can be like anything you want. But there are various examples in which you can think of, which will have this phenomenology.
I'll ask you later.
Right. So another thing which may not be super interesting for BSM, but in some sense, like maybe underlines again this point about having features being something very important, is the example where you have some primordial features, which are some kind of wiggles in the linear power spectrum coming from inflation. And all that I'm showing here again is that what happens if, for example, frequency is small, such that these features that basically do not exist. You have very broad features which are hard to disentangle from some nonlinear evolution, versus, let's say, large frequencies where the features are prominent and there is no, again, astrophysical mechanism to generate them. And you can see that, again, the discrepancy between some kind of ideal case and the worst possible case here is much smaller than here. And again, it just tells you that looking for new physics, which will leave some imprint, which has some feature, then is very interesting because galaxy surveys have enough statistical power to give interesting constraints. Okay, that is, I think, the main message of these examples. And finally, another famous example is this Cosmological Collider, which again provides one particular feature, and this is Michael, what you asked. So you see, if the particles are more massive than certain threshold, then you're going to have these effects that you can thermally produce them in the sitter. You produce virtual pair. There are some oscillations of the wave function of these massive particles, and they eventually decay into inflatons. And if you calculate the 3-point function again in this soft limit, you will find this particular behavior, which is model independent, which has this particular scale dependence. But now you see it has a q to the 3/2, not 1/q. It's in this sense, it's bad because this is then means that there is some suppressing factor, and this is not surprising because this factor exactly comes from the fact that massive particles dilute as a cube in the expanding universe during inflation. But then what is interesting is that there is also this particular scale dependence and angular dependence, which basically tells you what is the mass of the particle and what is the spin. So, in a sense, if you ask yourself generically some type of non-Gaussianity, which is equilateral type, can I measure? The answer is not so well because there are many systematic you're fighting against. But if you look at this type of examples, then because of these features, then the constraints look much better. And so we have some hope to give some, to basically put some reasonable limits from galaxy surveys in this kind of examples. All right, so I think that since I'm running out of time, I will just stop here and give the conclusions. Thank you.
Thank you. Any further questions from here or from the Zoom? I actually have a question about the,
Yes.
I'm still confused. So this equivalence principle testing,
Yes.
that's only if the force is unscreened, right? It's not just long range force. It's the
Right.
fact that the
It must be unscreened.
it must be unscreened.
Or maybe if you want, for instance, in various extensions of what people call modified gravity, like Galileans or things like that.
Sure.
So then you have screening which can depend on various properties, either of the environment, or like which depends on the potential or density, etc., or the mass of the object. And so, for instance, you can think about these two types of galaxies as being screened versus screened. So in that case, even if there is a screening, but there are some objects which are not screened, you will have the same effect. Except in Galileans, in which this never happens because there is a particular type of interaction which always has two derivatives of the gravitational potential, and you never generate these terms, unfortunately. But so for this particular example, it doesn't work. But let's say in some chameleon screening, of course, it will have chameleon type interaction. But of course, then, yeah. I'm not trying to, all the time I'm avoiding to give particular examples because my idea is to provoke you to think about new examples, which perhaps you like better than the ones that exist.
But just a simple like scalar force that works for this? Just the Yukawa force? Yeah,
well, I think that, yes, I think that people are already working on this. I think that it probably works, yeah.
I see Julian has a question.
Yes, Marko, if you would try to measure the squeezed bispectrum in future surveys, would you have enough lever arm to have Q and K1, K2 to be the extreme in the range of linear scale that you measure? Or would you need Q to be linear, K1, K2 to be nonlinear, and then suffering from issues of bias and nonlinear physics?
Yes, so I think that all that we need is a big separation, well, relatively big, even factor of 10 is already very big separation of scales. What we need is that Q is, again, in the linear or multi-nonlinear regime, K can be as high as we want. And the beauty of this approach is that, or this theorem, if you want, is that this nonlinear evolution doesn't matter. So you don't want to fit to your data in the usual sense. You just want to make sure, you want to project your squeeze limit bispectrum onto this particular template and see what kind of amplitude do you get. Now, of course, what will stop you going to very high Ks is going to be first of all, that they're very correlated at some point. So the covariance matrix will tell you that you don't gaining much information, and then there is short nodes. So when I mentioned these numbers, 10 to the minus 3 or so, this was done pretty naively back then in this old paper, but one of course has to reconsider these bounds. And also, I think that, of course, modifying this interaction this way will have repercussions also for the CMB and like other observables. So one has to do the whole analysis very carefully.
Thank you.
Yes, Davide?
Hi, thanks. I had a question about the very last slide when you were mentioning the Cosmological Collider signature. Could you expand a bit more about how the galaxy surveys could be better than the CMB? I don't know, maybe projection effects could be not as severe, although there is no linear physics, maybe that complicates the story.
To be honest, I'm not aware. I don't know. Maybe somebody knows. Like, I don't know what are the current CMB limits, if anybody did it at all. But I also I know that, for example, there was the group at Harvard who did some projections on what kind of amplitudes we can get. But I'm not sure. I don't remember on top of my head. I think that
it is at a more preliminary stage.
Right. I think that for sure for higher spin or like, let's say, larger masses, but of course it cannot be much larger than Hubble, because then you will have some suppression in front, unless you want to get rid of it in the DFT inflation and so on and so forth. I think that the more if the feature is more prominent, the large K structure by rule always wins because it has many more pixels, independent pixels. So usually the large K structure is not so powerful because many of these pixels, in a sense, are used to measure nuisance parameters, bias parameters, I don't know, whatever other things we have that we really don't know about galaxy formation, etc. But here, when we have a clear feature, all of that doesn't matter, and then all your constraining power goes into your feature. So I would imagine that there must be a range of parameters for which large K structure must be better. Yeah.
Okay, thanks for the nice talk.
Any more?
Naive particle theory question. So you showed us these surveys breaking the generalities in the CMB, but is also the opposite true? And this question is going the direction: do we need CMB stage 4, or are these guys powerful enough?
So now I have to be very politically correct. I think that it depends what do you want to do, because there are certain things that CMB can do. Let me go back to all the way to this example that I showed. For example, here, one of the things that we are kind of curious about, and it has consequences for whoever wants to modify early universe expansion history, thermal history, is this N-effective parameter, which parameterizes how much radiation you can have on top of the standard 3 neutrinos, 2 neutrinos and photons, etc. So the large K structure alone cannot measure this parameter well, so you have to get it from the CMB. But the point is that, again, if you do the CMB alone, it will not be as good as this. So you see, they're always in combination, they really like are very powerful. So I would say that, of course, that we still need CMBS4. Because there are parameters which are interesting, which we cannot get only from galaxies. And there are parameters which are interesting, which we cannot get only from the CMB and in combination. Because you see, both galaxies and CMB are observing things on the light cone at a particular redshift. And so since these distances are very different in the nearby universe, like low Z and high Z, as is the title of this week's theme.
There is the obvious point that the CMB is at a different time. But,
yes, but
how it's reflected in this time.
But it is reflected usually through the rotation of the contours, not always, and not for all parameters. But the generalities are different if you look at something nearby and far away on the light cone, and this is how you can gain a lot in combining the two.
We're just saying that they're actually different.
It's not only the direction. I think that the most interesting phenomenon, the most relevant thing is that the distance to the CMB is a complicated formula which depends on omega matter, blah, 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 and so on and so forth, Hubble, etc. And if you expand this formula around this particular redshift, you will see that, for example, omega matter H contour is very differently oriented simply because you're expanding around different Z than something which is at the low redshift 1 or 2. And I think that the fact that the angular diameter distance or luminosity distance is different in that sense, that the dependence on cosmological parameter is different, is what breaks the degeneracy most of the time. But there are also other things. Yeah.
Okay, if there are no further questions, let's thank Marko again.
Thank you.